Hello, my name's Ali Donaldson. I'm a professor at Imperial College London, and in this demo, I'm going to show you our mutation testing tool called Dredd. The idea of Dredd is that it takes a C or C++ code base and it allows scalable mutation testing of that code base by injecting all the mutants for a given source file simultaneously into that source file in a manner that allows them to be toggled on and off using environment variables. And the idea of this is that it avoids the need to recompile and relink the program when you want to test with a given mutant, and it also works at the source level, which is close to what programmers are used to working with, and avoid some of the unexpected consequences of doing mutation at the level of bytecode or IR. I'm going to start by showing you Dredd in action on a simple example. So here I'm in the root directory of the Dredd repo, and we've got an example subdirectory with a simple subdirectory that has got a program called pi.cc in it. So a simple C++ program that computes pi. Here's the source code for it, open in Visual Studio Code. And what I'm going to do is just compile with clang++ pi and run the program, and you can see the good old constant pi. So what I'm going to do is now run Dredd on this program, and we'll have a look at the output that Dredd produces, the effect it has on the C++ program, and we'll see some mutants in action. So to run Dredd, I'm going to give it the C++ file, and then dash dash to indicate any extra arguments that should be passed on to explain how this file should be compiled. Things like includes, don't need any here. So I'm going to run Dredd, and Dredd runs, it processes this file. And I'm now going to show you the source code, and it now looks unrecognizable. So if I scroll down to the bottom of this file, you can see that this main method, which called calculate pi, has been replaced with this body that does these things like calls a special function, Dredd enabled mutation, and calls functions like Dredd, replace expression, double, etc. And the idea of these are that when we run the program, we can optionally set an environment variable saying that a given mutant ID is enabled. And these wrapper functions like Dredd enabled mutation and Dredd replace expression are going to query the environment variable that explains whether a mutant is enabled. And if a mutant is enabled, they will make the program behave as if that mutant had been applied to the source code text of the original program. And if no mutant is enabled, then the program will behave as it originally would have. So in this demo, I'm not going to try and explain how all those wrapper functions work. The details of that are in the paper, but I'm going to show you Dredd in action. And I should say, a human should never have to look at this mutated code. This is the effect Dredd has on the program, but the programmer, the tester, shouldn't have to actually look at this output. So first of all, I'm going to compile the program again, and you can see that it compiles just fine, but it gives us some warnings. It has a warning here saying non-void function does not return a value in all control paths. This is because Dredd uses instrumentation to mimic statement deletion. So some statements, including return statements of functions, are now guarded by conditionals so that if an environment variable for a given mutant is set, those statements will no longer be reachable. And this can mean that return statements that would have unconditionally returned from a function now only conditionally return. So those warnings are fine, they need to be ignored. If we run the program, we should see it still computes the good old constant pi. But now what we can do is we can set a mutant to be enabled by using this Dredd enabled mutation environment variable. And if I set an example mutant like 82, for instance, then we see when the program runs, it computes the value 0. If I set the mutant to be 88, then the program computes the value 4. If I set the mutant to be 16, then the program appears not to terminate. Looks like this mutant has introduced an infinite loop. And if I would set the mutant ID to be, say, 24, then we get the value pi computed as before. So this mutant hasn't had any effect on this execution of the program. So this is showing you Dredd in action on a very basic code base. And I want to show you that actually, if I just back out of that change to pi, if I remutate this program, so I say Dredd pi.cc, I can pass another argument, which is mutation info file, and the name of a JSON file. And now here I'm telling Dredd, mutate the program and write information about all the mutants that were introduced into this info.json file. So I'm going to do that, and now in Visual Studio Code, I'm going to open up info.json for us to have a quick look at. So again, a human shouldn't need to look at this file. This is a machine readable file, but it's a long file that's got details about all the mutants that were applied in the program. So you can see things like replace with 0, replace with -1, scrolling down a bit further, replace with not equals, replace with less than equals. And the point of this JSON file is that we can use it to understand the mutants that Dredd actually applied. So for example, we can say query mutant info, we pass in info.json, and we can say largest mutant ID. And this tells us that the largest mutant ID is 108. So Dredd injected 109 mutants into this source file. And then we can also understand the effect those mutants are mimicking. So what would we have had to have changed in the source code of the original program to get the effect of one of these mutants? This is a bit more of an involved command. What we do is we say, again, query mutant.info.py, we pass in info.json that's got information about the mutants, and then we need to pass in both a non-mutated and a mutated version of the system under test, so that Dredd can tell us how the mutant has affected the original source code. So this path prefix replacement argument takes two parameters. It takes a prefix to the mutated code, which is Dredd examples, and it takes a prefix of the mutated code, which is examples original. So that's just another checkout of the project. Then I can say show info for mutant 88, for example. And what this says is that mutant 88 replaced original expression sum with the replacement expression 1.0, and this occurred at simple.py, line 26, column 10, to line 26, column 13. And if I go to Visual Studio Code and open up the original version of Pi, we can indeed see that line 26 has got this sum. So this mutant replaced that sum with 1.0. Excuse me, that's the wrong line. This is line 23. And of course, I couldn't replace this sum with 1.0 because it's an L value. But here on line 26, this R value sum is replaced with a constant 1.0 by that mutant. Let me show you another one, the infinite loop mutant we looked at before, mutant number 16. So this is replacing the expression D with the expression 1, and that's at line 21, columns 19 to 20. So this is replacing this D with 1. So you can see this would indeed introduce an infinite loop into the program. And as one more example, why don't we have a look at the mutant 24 that had no effect. So this was replacing D less than this big number here with D less than equal to this big number. And this is at line 21, columns 19 to 30. So this is this constant here, which is 1 million. So 1 million, the less than check has been replaced with a less than or equal to check. So this is just making calculate pi go one step further, which hasn't had an effect on the result. Okay, so that's Dredd in action on a simple example. And now what I want to do is show you Dredd being applied to a library. What I've got in this math directory is a mathematics library that provides a number of very simple functions, number theoretic functions, trigonometric functions, etc. I'm not going to show you the source code of these don't matter for this simple demo, but what I want to show you is that we've got a CMake lists file in this directory, and we've got another CMake lists file in the math directory. So this is a project that's actually configured using a build system, and we'd like to apply Dredd to this project. So first of all, what we need to do is get the project ready to be built using the build tool. So I'm going to run CMake, specifying the current directory as the source directory, and say that I want the build to go in a build directory, and that I want to use Ninja as the build tool. And then I'm going to also set this flag called CMake export compile commands, set it to on. And what this is going to do is tell CMake to emit a compilation database for this project. So when I run CMake to configure the project, then in the build directory, you'll see there's this file called compilecommands.json, which is a compilation database for this math project. And if we look at the compilation database, we can see that it's got entries for all the files in the project. So for example, here's an entry for exp.cc. And what this does is it shows the compilation environment required to compile that file, which critically includes things like the include directives that you need to pass for the compiler to make sense of this file, and also pre-processor directives with the -d flag. And compilation databases are essential because if we don't actually know the include paths or preprocessor directives for a source file, then the code in that source file is actually incomplete and can't be statically analyzed. So with this compilation database, we can run Dredd in a sensible way on this project. Let me first show you what happens if we run Dredd on this project without the compilation database. If I just say Dredd mutation info file info.json, and I'm going to pass in all of the source files in the math directory. So I can say find math. I'm going to say type F name star.cc. Then what we'll find is we get lots of errors, fatal errors, Dredd saying that this file is not found, x.h, this file is not found, trig.h. So Dredd's not managed to compile this successfully. I'll just check out math to back out of any changes that I might have made. Okay, no changes were made because the compile command failed. Now if I run Dredd again, and this time I pass in a compilation database, so I use -p and the directory that contains the compilation database, then we can see that Dredd does mutate all of these files. And if I do a git diff on math, on the math folder, and just scroll through the diff, you'll see that Dredd's injected lots and lots of code to handle replacing statements with mutated versions. And this code is kind of unrecognizable from the code we originally saw, but it doesn't matter because a human doesn't need to look at this. So the Dredd source level transformations have been applied to this whole library. So now what I'm going to do is I'm going to run cmake build to build this library. And we can see we get lots of compile warnings because of the transformations Dredd have made that lead to, for example, control reaching the end of non-void functions. And that's expected and that's okay. And we can then check that if we run the test suite for this project without any mutations applied, things work out. So I run math test, which is the command for running the test suite, and you can see that all the tests very quickly pass. But what I might want to do is, for example, enable a particular mutant. So maybe I can say Dredd enabled mutation equals mutation equals 24. And then we can see here that one test failed. So the ceiling test handles integer input failed when I ran Dredd with that particular mutant. Let's try another one, 32. Then again, the ceiling test fails. Let's try another one, 88. Then we can see, in fact, all tests passed with that mutant. Maybe it's an equivalent mutant. And maybe let's go for mutant 150. And in this case, we get quite a few different failures throughout the project. So you can see this is an example of using Dredd to enable different mutants to understand which ones survive the test suite versus being killed by the test suite. And we could use the command I showed you earlier to actually understand how many mutants there are and what source code changes those different mutants are encoding. Now, suppose we wanted to try to use Dredd for mutation analysis. Quite deliberately, we've designed Dredd to be totally decoupled from any individual testing tool. Dredd applies the mutations and through the JSON file gives information about all the mutants that are encoded in the codebase. And then that gives flexibility for people building tooling on top of Dredd to get what they want from the tool. They might be combining Dredd with Fuzzer. They might be combining with C-test or with Google test. Rather than making Dredd fit with one specific test infrastructure, we've just made Dredd be a bit like a toolbox with a cord hanging out, so you can plug it into whatever workflow you're using. Let's say that we wanted to assess the extent to which Dredd could could introduce mutants that can be killed by all of the X tests in this test suite. So with this test suite, we can, if we just run the test suite with no mutants, then we can use the Google test filter command. We can say gtest filter equals exp test.star. And that is, excuse me, I must have written this command slightly wrongly. Gtest underscore filter. Let me see. Gtest underscore filter, missing T there. There we go. You can see this runs the tests under the exp test part of the hierarchy. So suppose we wanted to try and see which mutants those tests would kill. It would be useful to first of all know which mutants actually get reached by those tests. And we can do that by mutating the source space in a way that uses a different instrumentation that just gives the IDs of all the mutants that get reached during execution without actually enabling those mutants. So I want to show you that next. What I'm going to do is I'm going to go back one level and into math tracking, which is another version of the math source code, which I'm going to mutate with Dredd, but in a different mode, which is going to enable emission of all the mutants reached during a test run. So to get this going, I'm first of all going to run that same cmake command to get the project ready to be built. And then I'm going to run Dredd as before, except this time I'm going to pass another argument, which is, in fact, let me do a Dredd help to find the argument. So Dredd help. The argument I need is called only track mutant coverage. So this is just going to track the mutants that are actually reached during test execution. So if I get the old Dredd command back, and this time I'm going to plug in this extra argument, only track mutant coverage. This is going to mutate the source base, but now the mutations that have been applied are not going to actually change the behavior of the program. They're just going to lead to the IDs of all mutants that have been reached being written to a text file controlled via an environment variable. So what I can do is I can run the application again. So I can say build math test with the Google test filter for exp test. So I need to build the project first. So cmake build. So this will build the project in this mutant tracking mode. And then I can run these math tests and they will pass. And I can run them again. And this time I can say Dredd mutant tracking file equals tracked.txt. And what that will do is it will write all of the IDs of the mutants that were reached during execution of this test suite to tracked.txt. So if I do cat sort unique on tracked.txt, then you can see a bunch of mutants got reached. And if I count how many, you can see 103 mutants got reached when executing that test suite. And now what we could do using a script is we could go through just these mutants, the ones that are actually touched by executing that subset of tests, and using the properly mutated version of the code base where we can enable those mutants, we can assess whether or not those tests kill them. So for example, this mutant 345, if I go back into the math directory and I run the test suite again, but this time, because I'm in the properly mutated version of the source tree, I can say Dredd enabled mutation equals 345. Then we can see that this actually causes a test failure. We get an illegal instruction. So this, this mutant is killed by those tests. Let's just take another one, 308, as another example. Then we can see that 308 leads to a number of failed tests. So indeed, the test suite kills mutant 308. So you can use these two different modes of Dredd, the mutant tracking mode that tells you which mutants get reached by execution of a test or tests, and then the proper mutation mode to try and kill mutants. You can build scripts that use those in combination to determine how many mutants get killed by a given fuzzer over a given time period, or by a given test suite, or in any flexible way that you like. The final thing I want to show you is Dredd in action on a larger source code project, which is the Clang LLVM compiler, a really large C++ code base. I'm going to go to the root of my Dredd demo folder, and I've got here LLVM 22.1.7 mutated, and ahead of time I mutated and built the compiler, mutating all of the C++ files under the transforms directory of LLVM. So if I say here, find LLVM lib transforms name star.cpp, you can see there are quite a lot of C++ source code files here. And if I use word count, you can see that there are 319 C++ source files, all of which have been mutated. And we can have a look at the largest mutant ID by using the query mutant info script. I'm going to pass in mutationinfo.json, which is the JSON file I generated when I mutated these files, and I can ask for largest mutant ID. And this will take a little while because that JSON file is enormous. It encodes the details of a huge number of mutants, and in fact we can see that there's 705,000 or so of the mutants. So what I want to do now is show the effect of compiling a C program with the Clang LLVM compiler with mutants enabled. And I'm going to get that C program from the CSmith random program generator. I'm going to say here CSmith, which is a version I built earlier, with the seed 42, which I tried earlier. I'm going to put this into prog.c. So the CSmith generator runs and produces prog.c, which is a random C program we can have a look at here. It's very long, very crazy looking, very good for finding bugs in compilers. So that's our CSmith program. And first of all, I want to look at the effect of mutation on the compilation of that program. Let's have a look at which mutants or how many mutants are actually reached when we compile prog.c with our mutated compiler. What I'm going to do to assess that is in the directory LLVM 22.1.7 tracking, I've got a version of this compiler mutated and built in the manner that actually just tracks which mutants were reached during execution. So I'm going to use that version of Clang to compile prog.c. I need to give a couple of include directives to get this to compile correctly. So I need to say that CSmith's runtime is included and also the version of CSmith's runtime from its built directory. And this will lead to the prog.c being compiled. And I'm going to say that Dredd mutant tracking file is going to be tracked 0.txt because I don't have any optimizations enabled. You can see there are lots of warnings generated, which is normal when you compile a CSmith program. And if I run word count on tracked 0.txt, you can see that 494 mutants were reached in all of the optimization files in the LLVM compiler when compiled in this CSmith program. So not very many, but that's not surprising because we compiled with no optimizations. If we crank up the optimization level to 0.1, then we would expect to see a larger number of mutants reached. You already see 62,000 of them being reached. Crank it up to 0.2. 100,000, and if we go right up to 0.3, then we see 105,000 mutants are covered when we compile this single CSmith program with the mutated Clang LLVM compiler at optimization level 0.3. And I want to show you the effect of some of these mutants. These are some mutants that I tried out earlier, so I didn't just kind of stumble on these by lucky chance. This is pre-prepared. So I'm going to this time compile using the version of Clang that's in this current directory, which is the properly mutated version of LLVM. In fact, I will run the previous command, but instead of going to the version of LLVM in the tracking directory, I'm going to use the version in the current directory. So, and I'm going to keep 0.3 as the optimization level. So if I compile this program with 0.3, and I'm going to call this regular, meaning this is the version compiled with no mutants enabled. So I compile that program and run it, and I get this checksum computed by CSmith. This is the way CSmith works. At the end of the program, a checksum is printed out. Now what I'm going to do, I'll output to mutated, is I'm going to say Dredd enabled mutation, and I'm going to enable mutation 11701, and bang, here we get a compiler crash. So it looks like there's a bug in the compiler because a mutant has been enabled that's triggered this crash. Let's try another one. Let's try mutant number 457008. This one triggers another error, so we can see an error in backend, unknown instrumentation function, empty name. So this is another synthetic error introduced by the Dredd mutation testing tool. Now what I want to do is show you simulated miscompilation. So here I'm going to enable mutant 428672. And this time, the compiler appears to have worked successfully. I want to remind you, when I run the regular binary, the binary compiled with no mutation, we got just this checksum here. Whereas if I run my mutated binary, you can see we actually get a different result. We get all this extra output, checksum after hashing each element of various arrays. So this is output CSmith could produce, but it shouldn't produce in the manner that we've run the compiled program, but the mutant has ended up changing something so that this extra output has been produced. So this is showing a case where the mutant didn't crash the compiler, it led to the compiler producing the wrong binary, and then when we run that binary, we see an output that doesn't agree with what we get when we run the binary compiled by the non-mutated compiler. So this mutant simulates a miscompilation bug. And finally, I'm going to show you that if we compile with the mutation 428686, then compilation proceeds to some extent, gets through the front end of the compiler, but we wait and wait and wait and wait and wait, and nothing happens. So this is an example of a mutant that's introduced an infinite loop in the compiler, and we would detect this mutant as being killed by compiling with a generous timeout and determining the compiler is not actually finishing the job. So I hope you've enjoyed that overview of the Dredd mutation testing tool. It's an open source tool on GitHub. It's actively maintained, and if you'd like to get involved, we'd be delighted to hear from you. Thank you very much.